Hello again. This is Math 2232 coming to you from the College Edu page. The title of this lecture is Power Series. As always, be an attentive learner while watching these videos. By way of introduction, in this lecture we'll give a definition of a power series as well as the definition of the associated radius of convergence and the associated interval of convergence for a power series. We will also illustrate how the ratio test and root test can be used to determine the radius and interval of convergence for a power series. Previously, we spent a lot of time talking about series and only a couple of exceptions. We spent most of our time talking about if the series will converge or not. Now it's time to start looking at specific kinds of series, and we will eventually reach the point where we're talking about some very important and deep applications of series. So in this lecture, we'll start talking about a power series. Here's a definition. A power series about A. Now this is about a point A, and this is a point where we have some interest in what's happening near A. So a power series about A or centered at A, or just a power series, is any series that can be written in the form of the summation n equals 0 to infinity of Cn times x minus a whole to the n. Now Cn is a constant, n is the index, and x is a variable. So you see this power series is a function of x. For example, we could call it capital G of x. So this depends on what x is. Also, you should note it resembles an infinite polynomial with, as we shall see, some very similar positive behaviors, just like polynomials. So A is a point, and Cn are the numbers. The Cn's are often called the coefficients of the series. The first thing to notice about a power series is that it is a function of x. We already talked about that. That's different from the other series we've looked at to this point. In all the previous lectures, we've only allowed numbers in the series, and now we're allowing variables to be in the series as well. This will not change how things work, however. Everything we know about series still holds. In the discussion of power series, convergence is still a major question that we'll be dealing with. The difference is that the convergence of a power series will depend on values of x that we put into the series. A power series may converge for some values of x and not converge for other values of x. Before we get too far into power series, we'll introduce some more terminology. First, as we will see in the examples we do, we're going to be able to show that there is a number, capital R, so this is a number, so that the power series will converge for the absolute value of x minus a less than R, and it will diverge for the absolute value of x minus a greater than R. This number is called the radius of convergence for the series. So the radius of convergence is a number associated with the series. Note that the series may or may not converge if the absolute value of x minus a is equal to r. What happens at these points will not change the radius of convergence because the open interval from 0 to 2 is the same length as the closed interval from 0 to 2. Think about what I just said. Secondly, the interval of all x's, including the endpoints if need be, for which the power series converges, is called the interval of convergence of the series. So the radius of convergence is a number. The interval of convergence is an interval along the real line, and it is centered at A. Now these two concepts are fairly closely tied together, however. If we know that the radius of convergence of a power series is R, then we know this is the absolute value of x minus a is less than r, and that means that x is between a minus r and a plus r. So if this is true, the power series is going to converge by definition. If this is true, that is, x is less than a minus r or greater than a plus r, the series will diverge. The interval of convergence must then contain the interval a minus r less than x less than a plus r, since we know that the power series will converge for these values. We also know that the interval of convergence can't contain x's in these ranges x less than a minus r or x greater than a minus r, since we know the power series diverges for these values. Therefore, to completely identify the interval convergence, all we have to do is determine if the power series will converge at the endpoints, x equal a minus r and x equal a plus r. We will test this convergence separately. If the power series converges for one or both, or none of these, we'll either include or exclude them in the interval of convergence. And just before getting into the examples, let's look at the convergence of power series for the case of x equal a. Well, if you put x equal a, all of these terms are 0. And here we're going to say, and this is 0 to the 0. And 0 to 0, we're going to take by definition to be 1, although 0 to the 0 power really isn't 1. And so we're going to call that 1. So this is going to just be C0. So you see, a power series is going to converge for x equal a because it's just going to be the first term. And note that we had to strip out the first term. It was the only non-zero term in the series. It is also important to note that no matter what else is happening in the power series, we're guaranteed to have convergence at x equal a. The series may or may not converge for any other value of x, but will always converge for x equal a. Okay, so let's go and work some examples then. So here we have a series. This is a summation from n equal 1 to infinity of minus 1 whole to the n over 4 to the n, and this is x plus 3 whole to the n. And this is a power series. Here are the cn's, and this is x minus a minus 3 raised to the n. So the center of this is at minus 3. So let's see how you did. I should have put a little symbol here for you to work on this, but I think you know that by now. So we know the power series will converge for x equal minus 3 because it's just going to be the very first term. And in fact, it's not even going to be the very first term. It's going to be 0 because the rest, all of these terms, we're starting at n equal 1. So all of them will be 0. But that's it at this point. We know that we'll converge for x minus 3, but we want to determine the other x's that will give us convergence. So what we're going to do is we're going to consider and the best test to use are almost always the ratio or root test. So most of the power series we'll be looking up are set up for one or the other of these. In this case, we're going to use the ratio test. So what we're going to say is, all right, what is the limit of this expression here? What is the limit of an plus 1 over an, because this is the ratio test. So here is an plus 1. Now, remember, I'm substituting for n plus 1. So I get minus 1 to the n plus 1 instead of n. This is x plus 3 raised to the n plus 1, and this is 4 to the n plus 1. So that is a to the n plus 1. Now we're going to divide that by a to the n, which is this, but when you divide by this, you invert it. So this is 4n minus 1 to the n, and x plus 3 whole to the n. And we have absolute values around this. So you see we're using the ratio test. Now what will happen is the minus 1 to the n will cancel into this and give us a minus. Because this is minus 1 to the n plus 1 over minus 1 to the n is minus, but that minus is going to drop out with the absolute value. Here I have x plus 3 to the n plus 1 over x plus 3 to the n. That is just going to be x plus 3. And here I'm going to have 4 to the n over 4 to the n plus 1, so that is 4 to the n. So you see this simplifies into this expression. So what we're going to have then is L is equal to, now the absolute value of x plus 3, I guess we're saying up here, notice that x is not dependent on the limit. That means x is not a function of n, so it can be pulled out here, and the whole absolute value of x plus 3 can be pulled out, and we're keeping the absolute values there. But what is left then is the limit as n goes to infinity of n plus 1 over 4 to the n. Well, that's going to be 1/4 in the limit. We've done that many times. So L is equal to 1/4 the absolute value of x plus 3. If we are forcing this to converge absolutely, we're going to say, let's force L to be less than 1. So we take this to be less than 1. And that means we'll multiply both sides by 4. The absolute value of x plus 3 is less than 4. The series will converge there. We also know if L, this, is greater than 1, we know that multiply both sides by 4, that the absolute value of x plus 3 bigger than 4, the series will diverge. So you see, we know then that the absolute value of x plus 3 is less than 4. That means x plus 3 is between minus 4 and 4. Subtract 3 everywhere, and so the interval convergence will contain minus 7 less than x less than 1. And notice that this is of a length twice what is going to be the radius of convergence, the 4. Okay, so we have that. That's an interval of length 8. But what we don't know is what happens at the endpoints, x equal minus 7 and x equal to 1. We have to test those separately. But we know here that r is 4 because r is this magic number here. So we're going to test these separately. So what happens when x equal minus 7? Now I'm going to remind you that this is the series. So when I put minus 7 in here, I'm going to get minus 7 plus 4 is negative 4 to the n. So that's what we get for our series. But this is minus 4 to the n over 4 to the n. That's minus 1 to the n. N is just n. And this is 4 to the n, but that's 4 to the n. Those cancel. And when I take minus 1 to the n times minus 1 to the n, I get minus 1 to the 2n, which is 1. So you see, when I simplify this for x equal minus 7, I get the summation n equal 1 to infinity of n. Now this is divergence because by the divergence test n goes off to infinity, and that's not equal to 0. So it diverges at x equal minus 7. Let's look at the other endpoint, x equal 1. In this case, we substitute in here. Now we're putting 1. When we put 1 in here, we'll get 4 to the n. So we have 4 to the n over 4 to the n, and this is minus 1 to the n. Now this also diverges because this bounces back and forth. The limit just doesn't exist, and so it doesn't converge to 0. So in this case, it will not converge at either endpoint. We tested them both. So the interval convergence then is minus 7 less than x less than 1. Now in that example, it didn't converge at either endpoint, but sometimes that'll happen, but it doesn't always happen. Sometimes it converges at both, sometimes it converges at one. Let's look at another example. Determine the radius of convergence and integral convergence for the following power series. So this is summation n equal 1 to infinity, 2 to the n over n, and this is 4x minus 8 whole to the n. So we're going to use the ratio test again. So L is equal to the limit. This is a n plus 1. Again, I'm replacing everything with n plus 1. Every n is being replaced by n plus 1. And then we're going to divide this by a n, which is this, but I turn it upside down to multiply, so I have this. Now I'm going to observe some cancellations that will happen. I have 2 to the n plus 1 divided by 2 to the n. That's going to give me 2. Okay, I have n, and then this is 4x minus 8 to the n plus 1 over 4x minus 8 to the n. So that's just going to be 4x minus 8, and that's going to be n plus 1 in the denominator. So that is what I have so far. Now I'm going to realize I'm going to factor out the 4x minus 8 and take the absolute value with it because that doesn't depend on n. So I jerk that through the limit sign. So this is the absolute value of 4x minus 8. And this is the limit as n goes to infinity of 2n over n plus 1. But this is going to be 2, this limit, and that's 2. But also observe that, well, okay, so 2 times that, we're forcing that to be less than 1 for the series to converge. If it's greater than 1, it diverges. That's the ratio test. Now observe that we really want this to be, so the radius of convergence is 1 over 8, and we can factor out a 4 from this and divide by this, so we get minus 1 over 8 is less than x minus 2, less than 1 over 8, and we can add 2 to everywhere, and we get x is between 15 over 8 and 17 over 8. But now we have to check the endpoints. Again, we're checking them in the original series over here. So what happens if we have 15 over 8? Well, when we put 15 over 8 in here, that's going to give us 4 times 15 over 8 is 15 over 2. So this is what we have. And when we subtract that, we're going to have minus 1/2 to the n. So this is going to be 2 to the n. This is going to be minus 1 over 2 to the n. The 2 to the n's are going to cancel, and we'll get n equal 1 to infinity of minus 1 to the n over n. But this is our old friend, the alternating harmonic series, which we know this converges because of our work on the alternating series test. So we know that this converges. So it converges for this endpoint. Let's check the other endpoint, 17 over 8. Again, we're substituting into this. So we substitute 17 over 8, but when we multiply by 4, we'll get 17 over 2. That is going to be 1/2. And so now we're going to get 2 to the n over 2 to the n, and we see that we end up with the harmonic series. Make sure you follow these calculations. And this is the harmonic series, so we know that this diverges. So you see the power series converges for one of the endpoints, and so the interval of convergence is going to be 15 over 8. It's going to be bracket 15 over 8 to 17 over 8 open parentheses. And that is the interval of convergence. Here's another example. Determine the radius of convergence and interval of convergence for the following power series. Now this is the summation from n equals 0 to infinity of n factorial. We talked about what that was. And this is 2n plus 1 to the n. Okay, let's start doing the ratio test. So we'll take this and we'll put a sub n plus 1. So there's n plus 1 factorial times 2n plus 1 to 2x plus 1 whole to the n plus 1. And now we're just going to divide by the other. But now when we look at this is n plus 1 times n factorial. The n factorials will cancel, and the 2x plus 1 doesn't depend on n, so I can pull it out of the interval. Now here it's important that you really think about this. If x is equal to minus 1/2, then this converges. But otherwise, this is going to be infinite, because pick any number that's not 0. This limit goes to infinity. That means the whole limit goes to infinity. So what we have is L is equal to infinity, which is bigger than 1, provided x doesn't equal minus 1/2. Now this will converge for x equal minus 1/2. So this series will converge only if x equal minus 1/2. If you think about it, you already knew that. But from our initial discussion, every power series will converge for x equal a. In this case, a is minus 1/2. Okay, so the radius is 0. There's only one point. There is no radius, and the interval convergence is just the one point, x equal minus 1/2. Yes, the interval convergence is really a point. Another example, determine the radius of convergence and interval convergence for the following power series. This is a summation from n equal 1 to infinity. X minus 6 whole to the n over n to the n. Now this is not quite a factorial, but it grows very, very, very fast. So let's do the root test. So this is L is equal to x minus 6, and this time we have powers of n. Let's use the nth root test. So L in this case is going to be the limit as n goes to infinity of a sub n, and then we'll take the nth root of that absolute value. So when I take the nth root, I'm going to get x minus 6 over n. Now, if I pick any value at all here, and I'll pull out x minus 6 because it doesn't depend on n, any value, this always goes to 0, so this is 0. Well, L equals 0 is always less than 1, independent of what x is. So what will happen is the radius of convergence is r equal infinity, and the interval of convergence is from minus infinity to positive infinity. So these last two examples talked about if a series converges only for x equal a, then the radius of convergence is r equals 0. and the interval converges is x equal a. Likewise, if the power series converges for every x in the radius of convergence is r equal infinity, and the interval converges is from minus infinity to infinity. Let's do another example. Here we're going from n equal 1 to infinity. This is x to the 2n over minus 3 to the n. So we want to determine the radius of convergence and the interval convergence for this power series. Okay, now here a is equal to 0, but that's okay because this is x minus 0, so that's not really important for us to worry about. But the exponent is 2n rather than n. And so let's talk about what happens with L then. Now this also is set up, since we have nth powers, we're also going to use the root test on this. So L equals the limit as n goes to infinity of x to the 2n over minus 3 to the n, and we'll take the 1 over n root here. And again, remember we have absolute values. So this is going to be the limit as n goes to infinity of x squared over the absolute value of minus 3. This is x squared over 3. Now, this will converge if we have this being L being less than 1. And that means x squared is less than 3. But the radius of convergence isn't 3, however. The radius of convergence requires an exponent of 1, so we take the square root of both sides, and this converges when? The absolute value. And recall that the square root of x squared is the absolute value of x, less than the square root of 3. Remember, this is x minus 0. In absolute value is less than square root of 3. Okay, so the interval convergence is going to be minus square root of 3 less than x less than square root of 3. And we have to take the endpoints separately. So let's check the endpoints. What happens when we take x equal to minus the square root of 3? Now remember, this is what we have. So we're squaring minus the square root of 3. So what we get is that it's going to be 3 to the n over minus 1, and this is 3 to the n. So this is the summation n equal 1 to infinity of minus 1 to the n. But this just bounces back and forth between minus and plus 1. So by the divergence test, it doesn't equal 0. And since that limit doesn't exist, then it does not converge for x equal minus 3. Let's look at x equals 3. We'll plug it into this again, and we will get this, and this again is, it doesn't always have to be, but it is in this case, the summation n equal 1 to infinity of minus 1 to n. So neither one of these endpoints converge, and so the interval of convergence is minus the square root of 3 less than x less than the square root of 3. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.